Remember, you need to be a legitimate registered Zoom member before it allows you. Oh, yes, as Kate pointed out, thank you for mentioning that. Likewise for Discord, almost all the people who had problems with Discord, it was because they didn't have a prior Discord account. You should have a prior Discord account before um, we can, before it will allow you to become part of our Discord things. So for those, and I'll give a small introduction for those of you who are new. Again, a very warm welcome to this bootcamp. It is a very long bootcamp. It's 16 weeks. And that is the lower bound. Most likely, you'll be working on your project way beyond 16 weeks, more like 20 weeks or 24 weeks. In other words, it's quite likely that you won't be able to finish it before November end, right? It is intense. A lot of people, they get very, very enthusiastic, very excited about the project, and they finish it by end of December, end of January, or something like that. But shoot to at least finish it off before end of January, because the second boot camp will start thereafter. Um, there is a reason why it is so intense, because we want to make sure that you know the entire landscape of generative AI, properly know it. LLMs are changing the world. It is the single biggest thing that has happened in this decade, in the last 10 years. It is completely transformative. It is vitally important that we know it. It is turning the world on its head. It is writing code for us, writing poetry, writing articles, right? It is now even begun to write legislature, because it turns out lawmakers are heavily using it, right? And which is a bit disturbing, but it's happening. So we need to master this from the first principles deeply, not at the level of some Medium article, not at the level of some libraries that we just download and write 5 lines of code with, but how to build it up from the ground up. Now,
okay.
What did we?
Asif, sorry. Can I just interject one thing? You're saying that LLMs are writing law, legal essays and all that. I'm just applying for a job for a senior product manager. And based on the first interview that I had last week, I gathered what they are building and top of what they are building. And based on that, I pushed everything to ChatGPT 4.0. And along with it, I wrote the vision, the strategy, and I wrote ICP, ideal customer profile. I wrote a market narrative. Then I wrote a roadmap plan and make sure that SOC 2 and compliance and all of that can be taken care of. And I also went ahead and created how this product management will deal with the go-to-market. And I created a website for this. Okay, I'll send it to you.
Take yes, please share it with everyone.
Everything,
if it is
everything,
okay, yes.
Absolutely everything using ChatGPT, actually. Everything, start to end. And it actually also helped me build a website, actually.
Excellent. So guys, there you are. You have a developer, writer, thinker, strategist all rolled up in one. Maybe it's time to go back to farming.
Intern actually said plumbing is also one of the choices. Plumber.
You still need to learn. It's a very good question. Do you still need to learn Python? I assure you, you do. See, guys, here's a good analogy for this. I'll just take a small digression. When computers came out and spreadsheets came out, people thought accounting is dead. Accounting is not dead. Accounting just doesn't do what it used to do, right? It used to be a lot about hand calculations. It's not about that, but the subject has evolved. In the same way, software engineers, and this was, by the way, one of the interviews, I believe, the CEO of Amazon recently gave, and he made this point, that software engineers will soon not be coding. Right? Does it mean they won't write any code at all? No, they would just be the people who are most qualified to write the right prompts that will help a LLM generate code. Because they know data structures, algorithms, they know the computer science subject. And so they know what is coming out is right, and they know how to navigate with the tool. Just like accountants are the best people who can navigate with the spreadsheets. So that is the world we are entering, and that world is ushered in with these large language models. So, with that bit of introduction, I would like to bring your attention back to the course. If you go to this course, you will notice, let me put on the hat because I see more things than you see. Obviously, as you can see, okay, by the way, you see all of these topics that you don't see? This is your future in this course. And it contains a lot of things. It goes all the way from uh, what you're doing now, semantic search, to RAG, to multimodal RAG, to hybrid search, to document AI, to diffusion models, segmentation, computer vision. Everything is in this course. It's a pretty long and intense, and at the end of it, the last thing you'll do is LLM for code generation. You'll realize that it writes very complex and much better SQL than you do. It writes much better React code than you do for UI, and it can take your code and find all the ways to improve your code. And you won't do it by using somebody else's library. You will be using a transformer and building these pieces up yourself, right? So there is a long journey that we'll do, but let me take on the student role and see how it looks to you. Oh, this looks like a much more manageable course now, right? So for today, right? So guys, the topic of last week. So first, what was the homework for last week? The homework for last week was to build a very simple semantic search engine. And I believe that document I posted to, where did I post it? Discord. It is on Discord. And I'll put a better written version out here. And the description of the, if you want a more detailed description of the project, it is in Searching for Meaning. Right? I hope you all read that. Those of you who are from the first week, read that. Those of you who are not, you should read that. The document that's posted on Discord is just a phased approach to doing this project. And we'll see how many phases you have done. Journey, and this is a long journey. This is an old saying from a philosopher that I like, Tao, who was, I believe, a contemporary of Buddha and and Socrates. Somehow within the same couple of 100 years, all of these people mushroomed across the globe. And he said a lovely sentence: "Journey of 1,000 miles begins with a single step." It's a famous quote, and I thought I would mention the entire quote because, as you'll realize, it's really apropos to your journey. A journey of 1,000 miles starts under one's foot. This is the exact one. It's been popularized to what we do. A tree with a full span's girth begins from a tiny sprout. A 9-storied terrace rises from a basket full of earth. A journey of 1,000 miles starts right at the foot, which is below one. To act, and so it goes on, to act with desires, to be agenda written, and the blah blah blah. So we'll leave the rest of it, but this is where it is, guys. Keep making small steps and you'll succeed. The recordings of last week's are here. I strongly encourage you to go through these recordings. People tell me that quite often, because of the stories I interject and the slow way that I speak, it is far easier or more bearable to watch my videos at 2x or 1.5x the speed. So you should be able to run through the videos pretty soon. One more thing, the transcript of the video, YouTube now very helpfully gives you the transcripts of the videos. The third thing, which I have not done, but you will see coming up, is one part of our EduTech. For each session, each video, a much more digestible 1,000 token summaries that are we have written, and those we'll be posting. So you can instead just read that. 1,000 token summary is something you can absorb in 10, 15 minutes rather than watch an hour and a half long video. And it will give you the gist of everything, or at least it could be the notes for you to go through. We went through the lab the last time, and it was about semantic search. I hope you remember that. And the Sentence Bird is the website, which is this website. I said the very, very first lab that we'll do is with this. If you look at the code here, you see that the code is very, very small. It is what? Exactly 4 lines of code. 1, 2, 3, 4. Right? And the second line is not really code. It is just data. So 3 lines of code. And isn't it impressive that in 3 lines of code, you could create an AI search engine? A tiny AI search engine, at least a proof of concept. So one of the assignments that I'd given is go master this website thoroughly, learn about AI search. And I'll give a quick introduction to it all over again. My apologies to those of you who came uh, last week that it might look a bit too repetitive, but please bear with me since so many people have joined just this time. Now, when you look at sentence embedding, you may think, which of the models should I use? It must be a question that must have occurred to you, right? You may have started with the mini model, which is good, which is quite good. But as the state of the art, I mean, this work is now 4 5 years old. In the 4 5 years, there has been a tremendous advance in sentence embedding technology. And as the state of the art moves forward, people have created better and better embeddings. At this moment, the Cohere's embedding and OpenAI and Microsoft and Google are the commercial ones who are competing with each other. But believe it or not, the best embedding actually does not belong to them. OpenAI is, I believe, not even ninth. It has sunk from ninth to 16th. The best embeddings are at this moment belonging to the mostly open source contributions, and we can go look at it. So at any given moment, you can go look at that. BGE. BGE stands for, I believe, the Beijing University's contribution. Stella is doing very well. GTE, another by the way, Quen is doing, Quen, as you know, is a competing model to the Llama, and by many people's account, much better than that.
Which one is that? Gwen?
Quen, Quen, Quen 2.
Gwen. Okay. Gwen,
Quen 2.
yes.
Quen 2, by the way, if you download Quen 2, you will see that Quen 2 is very competitive with Llama 3.1. And in fact, some would argue that it beats Llama 3.1.
And where does it come from?
I think either Korea, Taiwan, or China, somewhere, or
Okay.
one of these Asian countries. You can look up the exact roots of these models. So at this moment, in AI, there is a fierce everything. So the licensing is of all of them is very permissive, right? The only thing is that some models, when you try to download it, you won't get it from Hugging Face. It will say, okay, no, wait a minute, you need to go to OpenAI and pay them some money for it, right? So, like for example, now if you look at this list, and this is one of the things people don't realize that open source community is moving way faster than the commercial guys are able to run. Literally at this moment, in many areas, open source. So look at this. The first commercial thing that you see is Google Gecko, right? It's at rank 20. Then you notice that way down below is Cohere and Google again. And where in the world is OpenAI? Cohere again.
Hmm.
Somewhere in there, you will finally find uh, these models. So one of the lessons to learn is think twice before you start paying companies for something that might actually be inferior. This is an important lesson. All right, so that's a thing. Now I will start with the summary of what I taught last time, and this is again a review of last time. The topic last time was we started with the topic of what was the topic? Anybody remembers? Was that semantic search? Semantic search, yeah. So the idea or the use case that we started with in practical use case is the discovery of a whole way of doing what is called semantic search. The history of this is this. We talked about search engines, the basics of traditional search engines, what has dominated the world for decades. And for example, when you look at Elasticsearch or any one of these very mature industrial strength search engines, what they are, and uh, uh, in its most primitive form, obviously they have layers and layers of sophistication built on top of them. But foundationally, what they are is they are keyword. So suppose I have a word, the cow. Um, we'll take three sentences: jumped over the moon, one, two. We can say, or let's call it A, B, C. document C, the happy cows were grazing in the meadow. The children were playing happily, happily in the yard, in the playground. I just wrote three sentences, and I could add a few more. What you do is, and this is also called, um, this word is your keyword search, and we'll see why it is called keyword search or inverted index search. If you were to take any book on this field of search is called information retrieval, IR, information retrieval as a field. What IR is, what it says is, look at the text, highlight the words that are worth searching for. You don't want to search for the word the, over, and so forth, isn't it? Those are what are called stop words. You just filter them out. That which remains after you filter them out, then you reduce it to their canonical form, the standard form. For example, jumped, jumping, etc., can all be reduced to the word jump, isn't it? So represent them with a canonical form and pick the words that you really care about, playing happily in the playground. So let's start writing those. Cow, it is in document A, and the word, it is also in the document B. The word jump is in document A and or sentence A, and where else is it? Jumped is nowhere else, right? Moon, right? Moon is also in A, and if you were say happy, happy is in B and C, right? If you look at the word play, you would say just C, right? And so on and so forth. You can look at the word grazing, you would go with the word B, right? And now all you have to do is, what we do is we go to Google. We have been all conditioned to do this. You go to a search bar and you start entering your keywords. Isn't that the conditioning that we have developed because of the decades of this kind of keyword-based search engine? You enter the word. Suppose you were searching for cow and grazing. It would overwhelmingly say, oh, A, B, and B happens twice. So most likely I will start with B, and A is my second search result. Right? In very simplified form, this is your search engine, the traditional search engine that you are used to. The trouble with this search engine is, next time you lose your keys, try turning to your better half at home and just mutter the word keys, keys, and look at the stare that you'll get, right? You don't talk to each other using keywords, isn't it? What do? You say, I'm not able to find my keys. Do you know where it is? For me, by the way, that's a daily occurrence, even with tile. Right. So you we human beings talk in sentences. What is more, sometimes we don't know what the word we are looking for, right? Doesn't it happen sometimes that the actual word escapes you? You say, I'm looking, for example, you may go to a nursery and you can say, I'm looking for that tree. I don't know its name. It has this kind of a big leaves, right? And maybe pink flowers that hangs like a chandelier, or a yellow flowers that hang like a chandelier, or something like that. Are we together? Right? You uh, and then the nursery person may say, "Oh, you're looking for the jacaranda tree or something like that." So the trouble with keyword is you need to know what you're searching for. Sometimes we don't know what we are searching for, right? And so it doesn't become perfect. Now, with this as a background comes the concept of, and those are the limitations of a keyword search. So to summarize, the limitations of keyword search were that A, it does not align with human communication, uh, uh, or the communication as we know it, right? Hundreds of millions of years of evolution of languages through, I don't know, through various mammals and through us is not keyword based. Keywords is a very new form of thinking about search. Right? We need a more natural expression of what we are searching for. Yeah. Lemmatization.
Asif
Lemmatization
sir, one
simply
thing,
means yes.
some light is coming on your face. It is making it darker.
Okay, 1 second.
On the live, it doesn't look good.
Guys, if you don't mind, I'll turn off this light for remote participants. Please don't go to sleep on me.
Yeah, better.
Yeah,
It
I'll
looks
get you
good.
lamps. We have lamps. I'll bring the lamps out. Guys, bear with me. We have to set up the infrastructure. We'll do it in the break. So, what is lemmatization? Lemmatization is what I said canonization. Playing, play, played, play. Play is the lemmatization of it, or the root word, lemma. That's what it means. So, what happens is when you insert it into this table, you always lemmatize it. Or libraries do it. It's just a lookup. You maintain a long lookup for every word. What is its lemmatized version? There's a database for that. So, for example, singular and plural, right? So for horse, it's horses. For data, it's datum, right? Oh, that is there. The dictionary makers have already taken care of it. That's not even engineering. That's been done by the linguists and by the grammarians and things like that for hundreds of years. It exists. All right, guys. So, with that as a context background, we enter the world of a completely new thing comes out with AI called semantic search. Now, there is a particular architecture. By the way, did I last time remind me? Did I cover the transformer architecture as in attention is all you need? We did not, right? But we covered BERT and sentence BERT. But did I cover BERT also? Paper reading on BERT. Okay. So I will simplify it down because today I'll be doing attention is all you need. And because it's a foundational paper, what what these machines do is that BERT says, and these are, so I won't use the word BERT, but is generalization. I'll call it encoder, right? A transformer encoder. You give it two sentences, S1 and S2, and then you prefix it with a special token, CLS. But the point is, what comes out of this? So, what will come out? What is a sentence made up of? It is made up of words and punctuations. So, words and punctuations, you just call them tokens. Are we together? So, when the word token is used in this literature in our field, you could mean it could be the word or it could be the punctuation. Actually, it could just be a word piece. Uh, More technically, it gets even parts of a word also can be tokens. And that it turns out that from a technical perspective, it is more efficient to use word pieces rather than words themselves in some implementation. Right. So we will skip that. Yeah. So for example, unlikely, right? And uncommon. You notice that un is a prefix that's applied quite often, and it has a unique meaning. Is the negation of the word, the negation of whatever follows. So un is a word piece from that perspective, right? Un, and then common is another word piece in the uncommon. So you use with word piece, but let us just imagine that we have broken it down into pieces, the words. So what will happen is all these vectors for each token, a token TI goes in, and a vector VI comes out for that. But the vector that comes for this special token, CLS, it is your a final vector V. And now, what can you do with a vector? It turns out vectors are what you feed into. Well, see, machine learning at the end of the day is vector in, vector out. Always is something you have to remember, right? Now, if the vector is one-dimensional, well, it's a scalar, it's a number. But generally, all machine learning algorithms, supervised learning, prediction algorithms, are boxes into which vectors go in and vectors come out. Now what you can do is you can take this vector, the one that came out of this CLS token, and pass it through a classifier, let's say a machine that produces the probability. So VCLS goes in, and it will produce the probability or degree of similarity between S1 and S2. Right? It will produce a number between 0 and 1, which you can consider the similarity score between two sentences. Now, I hope so far we are together. How we do it, or how the machines do it, is one of the greatest revolutions or achievements of mankind at this moment. We'll cover that in the afternoon. Right? Is the discovery of the whole field of natural language understanding and transformers and so forth. We'll cover it in the afternoon. But just take it on faith that you can find the similarity between two. You can quantify the similarity between two sentences that is not keyword based. See, a keyword based similarity between two sentences could be as trivial as just counting how many words are common, right? What is often called the Jacquard distance, the number of common words divided by the total number of words, isn't it? So that would be a very primitive way of looking at it. Here, sentence similarity, actually, it's a machine that understands the semantic content of the sentence. Are we together? And the semantic content of the next sentence. And based on that, it determines how similar these two sentences are, which is a most remarkable thing. So you can produce a score function. You can produce a score function. Let me just use the word score. Score. There's a machine that produces the score, similarity score, between two sentences with a very high degree of accuracy. But the crucial thing is, the reason this works is because this is an understanding machine, language understanding machine. It understands language the way you and I understand language. Are we together? Now, compare it with, for example, when you do a hash table, does a hash table understand language? No, right? It is just a dumb thing. There's no intelligence in there. I'm saying that you have a box which has a natural language understanding, NLU, the word people use is NLU, natural language understanding. It understands the words, the sentences, and what is it that you're trying to say. You may not even use the word, but it has inferred that that's what you're talking about. This is how humans think. And we have created now, in the last few years, machines that can do that. And so to such a machine, if you give two sentences, well, obviously it should be capable of telling to what degree these two sentences are talking of the same thing, what degree of similarity there is, isn't it? So suppose I were to do a similarity score. Now, what is its impact on search engine? The impact on search engine is profound, because now, what is a search engine? In search engine, somebody gives a query, right? And you want to find all the similar documents in your system. And at the end of the day, using inverted search, inverted whatever, you're doing similarity search. That is information retrieval. But now if you have a much superior similarity score determining engine, what can you do? You can make in the same box, the first thing here, this part, you could replace with the query, isn't it? And the sentence 2, you can replace with a whole list of documents, D1, D2, D3. Suppose you have K documents in your corpus. Corpus means the set of all documents. Right? And so what can you do? You will end up with similarity score that will go query. Let me just write query and D1 all the way to query being compared to DK. Does that make sense? You can do that. And now, so what should be the search result? Just sort by score, descending. Highest score first. And you can pick the top K as your search results. Are we together? The top K of these are your search results. Oh, so it is pretty much you compare it to every document you have in your system. Right? So K here can be something like 100,000 or million documents. Right? You have a question? Yes. Types in a query, you go and compare against every document, find the similarity score, and then you come back. And therein you would realize that, my goodness, for every query, these days, can you imagine what is the size of the corpus the hyperscalers like Google have? Right? They're talking of hundreds of billions of documents. So it is infeasible because this cost, while this is very accurate, high accuracy, but it is prohibitively expensive. Very expensive to do, isn't it? Partly because to compare two documents, you're passing it through a very, very complex. So even if you were comparing one document, one query to one document, it has to go through the entire transformer layer, right? To produce this CLS vector, which will then go through a classifier to produce a score, similarity score. These models are, like in those days when they came out, were unbelievably large. I mean, by today's standard, we don't think much of them. They were 500 million parameters big, right? 500 million parameters. They were ginormous models. So when you do that, in terms of practical implications, your latency goes up. You have to wait a very long time for all of them to be computed, right? Each compute is expensive. You need a lot of hardware to do it. What happened is, it was just so overwhelmingly better than traditional search that the likes of Google and Bing, which were in an arms race to create the best search engine, nevertheless jumped into it, right? And they were trying to do clever ways of somehow not having to do so many comparisons. But they actually went. They said, okay, it may be expensive. We'll solve the hardware problem later. We'll make it better. We'll solve the algorithms later. But this is certainly the right way to move forward. Let's move forward with that. Most of you who have been doing searches should remember that around 2018, 2019, 2020, you should have suddenly seen, right before the pandemic, you should have seen a significant jump in the sort of quality of search results you were getting, right, for some time. So translations became better. Language translate. At one time, if you were having a bad day, right, and you were feeling low, all you had to do is go to Google Translate and ask it to translate something from your native tongue into English. And it would be hilarious enough that your depression would evaporate, right? So, but now translations have become very good. All of it is because of the transformer architecture, which Google discovered, and we'll talk about that. So now comes the question, how can we have the cake and eat it too? How can we do this computation lightning fast and not pay this massive computational cost? You realize, right? Because if there are K documents, this algorithm is order K, right? And because you have to compare the query to every K document. When you are sustaining hundreds of millions of queries or a billion query a day, it's not viable. A billion query compared against 100 billion documents, right? You're talking about quadrillions of computes. You just comparisons, just score comparisons. It's not feasible. So what can you do? Therein comes the main topic that we covered yesterday. We said, suppose you have a box into which what you can do is you pass it. It's called contrastive loss. Contrastive loss. There was a loss function. What is a loss function? A loss function is a measure of how wrong an algorithm is, how wrong a model is. Are we together? All models are wrong in machine learning. There's no such thing as a correct model. All of them are wrong. They're just wrong to lesser or greater degrees. The measure of their error is a loss. Loss of one intuitive way to think is how much of loss of understanding there is in the model compared to perfection, compared to getting all the answers right. So one trick that people use, and so pay attention for those of you who are new. I'll go over this slowly because contrastive loss, even if you have taken your Coursera's, etc., you may not have encountered that. The trick is very, very simple. What you do is you say, all right, suppose I pass a document. Let's say you know that you're supposed to give it sentence 1 and sentence 2. Sentence 2, right? So this is what what an encoder takes, isn't it? So in the beginning, what you do is you forget about sentence 2, right? You just give it a document di, some document, some sentence, right? Just pass it sentence 1. So when the output comes out, what will it be? It will contain the understanding of just the one sentence. The vector that comes out, it will represent the understanding of just one sentence. Let us say that the vector, and typically these vectors can be in 300, 500 dimensions, but we'll just pretend that these are in 2 dimensions, just for the sake of understanding it, right? So you pass in sentence 1, it becomes vector 1, right? So sentence 1 went into the encode, became vector 1. Are we together? Sentence 2 goes in, it also becomes vector 2, but you don't pass it simultaneously, right? You pass it one by one, V3. Now what you do, so far are we clear? To the encoder, we are just giving it one sentence at a time. And the second piece, it's because these BERT encoders, they take they take pairs. The second one you just pad out, blank it out. You say nothing goes in. So you keep on giving sentence. So you will end up with a whole bag of vectors, one for each document, isn't it? And now comes the training part of the machine. What you do is you take this transformer and you unfreeze the weights. Like, so one way of thinking about it is, imagine that you have, okay, guys, do you see this sound interface? Right? So the first rule is when a person like Sukhpal, a sound engineer, comes and tunes it up for this room. So all of these knobs, they have taken on certain values, right? Some are dialed up, some are dialed low. Now, what should you do? Next time you come in, you should randomly just change them? No, you shouldn't, right? Because you will lose everything that a sound engineer has set it up for. So that is saying you have frozen the dials, frozen the weights or the parameters of the model. You don't want to change it because it has been properly tuned to do one work. And so a transformer is tuned to produce these vectors. But what we are saying is we are going to do something dangerous. We are going to unfreeze those dials. So now you can happily again play with those dials, which is dangerous. But the contrastive loss function will come to our rescue. What you do is you deliberately create a data set which is made up of 2 similar sentences and 1 random sentence. Are we together? So you take a sentence A and you take something similar to A, and you take something that is random. This is your triplet. It's called triplet. So remember, the first 2 will be similar and the third one will be random. Doesn't have to be opposites. Remember, opposites are dangerous because opposites It's like, could be very similar. Like people often say, right? There isn't a psychologist. One psychologist once told me that what was it he said? A friend said, he says, it doesn't matter whether that guy is your friend or your enemy. That guy is still occupying space in your head. So in that
That's
sense,
funny.
don't take opposites, right? Just take a random sentence. That is easy. And now go create another sentence, B, SB, RB. And I can go on doing that and go do it for lots of times. Let's say 10 million or 100 million such records. Yes. I said that take a sentence. So I'll take a sentence. The children were happily playing in the playground. Then I take another sentence. Those kids were having fun in the yard. These two are similar. And then I can take a third sentence, which could be tractors have four wheels. It's
Just a
irrelevant,
question.
isn't it? So this is it. So what you can do is the hard work is actually picking these two pairs, building up a database of these two pairs. The third one is easy. You have scraped the web, randomly jump in and pick some sentence and attach it as the third in the triplet, isn't it? So you create this triplet data set. You create this triplet data set. What do we do now? And now you do something fun. Remember, you just unfreeze all the dials. You can take the machine and you can now retune the dials at that particular moment. It's called fine tuning. You took a machine that understands human language and you did something dangerous. It says, well, you need to learn some more. We need to put you through some college, right? And that process, which is called fine tuning, we will going through the fine tuning process. Or actually, I'll just call it training, but why am I not able to erase it? Okay, you do this thing. You make this, you say turn the dials in such a way that always the similarity, maximize the similarity score between A and SA and minimize the similarity between A and random A. And then do it for all of them, A and B, all of them, right? So you want to train the machine, turn the dials of the machine in such a way that when it produces the vector, what happens is that A, let's go here. If A is here, SA is somewhere nearby, and random A is somewhere here. If B is here, then SB is somewhere close by, and random B is maybe somewhere here, far apart, right? And if C is here, SC is somewhere nearby, and God knows random C may be somewhere else. And you get the idea, right? You put them close to each other. Now comes the similarity score thing. How can you find the similarity score? How do you know that two things are near each other in the vector space? Any ideas? Yeah. So why not Euclidean distance? Weren't you taught Euclidean distance in
Cosine
school?
distance will be higher.
What do you mean? Of course they work for vectors. Why not Euclidean distance? Puzzle. Why not Euclidean distance?
Yeah, Sif, it's Manju here. Euclidean distance, if it's high dimensions, right, they're going to be apart anyway, so it doesn't make much sense.
And why are they apart? Enlighten
Because
me.
it's n-dimensional, so the distance is going to be large.
Between any 2 points, huh?
Yeah.
Okay. All right. Anybody else would like to paraphrase? You're very close to the. You're absolutely correct. Okay. You had something to say, Abraham? Yeah. That's right. See, guys, high dimensional space are mysterious beast. Our intuition fails. See, we have evolved from fishes, let's say. And the only thing we know our human mind can grasp is 3 dimensions. Beyond 3 dimensions, we're just hand waving. Right. So what happens is the higher dimensions are mysterious things. I'll give you an illustration. Suppose I gave you a unit interval, 0 to 1, and I said randomly throw 100 points there. Right. What would happen is those 100 points will be very closely packed together on the number line, isn't it? They'll be pretty proximal to each other. On averaged, they will have 1/100th the distance between 2 points, a point and its nearest neighbor, isn't it? That's good. Now I make it 2 dimensions. What happens? These points begin to diffuse up. Right? Now they occupy space, more space, isn't it? So you realize that they have gotten a little bit far apart. And now I add a 3rd dimension. What happens? They will start diffusing into the 3rd dimension. And they will diffuse. If you have a random distribution of those points, they would have diffused even further from each other. In 3 dimension already, you can imagine that 100 points look rather far apart. Can you imagine what would happen in 1,000 dimensions? Right? That is one. There is another, actually, since we talk about dimensions and we won't get time to talk about dimensionality, higher dimensional spaces. Go ahead. They would all become remote from each other. Right? See, what happens is that the more dimensions you add, the more these points will diffuse away from each other, isn't it? See, in 1 dimension, they were only on a distance between a thing and its neighbor was just 1/100th. Right? Now, the distance, because it's 2-dimensional, you realize that now they are further apart. Any 2 points, a point and its nearest neighbor are a little bit further apart. In 3 dimensions, they are not on a plane. They are now in a solid cube, anywhere in the solid cube. Are you getting that? And so they are further apart. And as you go to even higher and higher dimensions, they keep moving further and further apart from each other. They're spread out. Somebody is saying something on Zoom?
Yeah, Asif, I was just trying to hazard a guess that it is about semantic. So it is the meaning that we are after. So if we are talking about 2 sentences, I'm a fool versus I'm a nincompoop, Euclidean distance-wise, they might be far apart, but semantically they are exactly the same. So the normal, the cosine similarity will be very.
No, hold on. I'm still building the argument.
Vector is very much the same.
Yeah. No, hold on. At this moment, I'll come to semantic similarity, but let's just understand how higher dimensions behave. Go ahead. That's the whole point. Human beings. Yes. Yeah. So the easiest way to think about this is that you take this solid cube and now you sweep it over time. Right? So time could be a 4th dimension. You realize that, imagine that the point could be, it will just comes into existence for an instant of time and disappears. So it could have been anywhere in 3-dimensional cube at any moment in time. So that is your 4th dimension. And now you realize that things are beginning to get rather sparse, right? And how do you imagine higher dimension? Well, you just mathematically, in your mind, you say logically, if I can go from R1 to R2 to R3, what prevents me from going to R4? And in fact, the nature, space-time, exists in 4 dimensions, right? There are theories of physics which started out, for example, one of the most popular theories, a string theory, it started out in 26 dimensions. So the joke was, it is in 26 dimensions because there are 26 letters in the English alphabet. The string theories were not amused. So, well, now it has come down. They have made it 10 plus 1 dimension, right? Or 10 dimensions of space and 1 dimension of time, right? Obviously, see, when you go beyond 3, human mind can only think mathematically. You can't see it. but it's a fact. So that's why it's important to develop intuition for higher dimension. Let me give you another intuition. See, okay, I'll take a little bit of a digression. I haven't talked about it the last time. Think of your neighbors, of your friends, schoolmates who are scattered all across the world. And ask yourself this question. Are they close to either a sea, a river, or a state boundary? How many of them? And you would imagine how very few should be like that. But actually, if you think of 10, you should come up with a number, something like four to six of them would be close to the boundary. Just do that experiment in your mind. Think, I'll give you 2 minutes to think through. How many of you agree with that? Yeah. So there's a very interesting reason for it. Actually, it's what is true in just 2 dimension on the surface of the earth becomes even more stark in that. See, imagine a unit circle, right? So you would imagine that if your world was a unit circle, if everybody lived on a disk, right? Your world was a disk, R2 or S2, then normally your friends would be uniformly distributed. You don't want the real estate price anywhere to blow up too much, right? So they're uniformly spread out. Now, if you ask, where do half my neighbors live? So let's look at that. You're in the center. Let us say that the complete distance is one unit. 1 unit could be 1,000 miles or something like that. Doesn't matter. 1 unit. At what distance R do 50% of my friends live? You would say, well, that is simply the ratio of the area, this area versus the whole. What is the complete area? Since you took the overall capital radius to be equal to 1, the total area is just pi, isn't it? And the area of this little circle is pi r squared. Pi r squared over pi is just r squared. And r takes on value from 0 to 1, right? A tiny circle is 0, a full circle is 1, isn't it? So you realize that if you want half your friends to be inside the disk, how far do you have to go to meet your friends? Let's say. So this has to be a half, isn't it? So r is equal to 1 over square root of 2. That is surprisingly 0.7. What does that mean? Means other half of your friends, they seem to be living within 30, much closer to the border than you thought, isn't it? Now what happens when you take a sphere, cubic space, 3 dimension? Like if your friends were birds and you were birds or little mosquitoes flying around, then to meet your friends, it would be r cube is equal to a half, your solid sphere, right? 3 dimension. And now r is equal to 1 over cube root of 2. What's cube root of 2? 1.3? 1.28 or 1.3? What is inverse of 1.3? Is 0.8 something? Guys, do that. What's the cube root of half? Right? Is it closer to about 0.82 or something like that, 82%? Which means that half your friends seem to be living even more closer to the border, isn't it? Now, what happens, and this is something that I want you to do, pull up your calculators on the web. Suppose I went to 100 dimensions, right? So now if this is there, r is equal to 1 over 2 square root or the 100th root. Can somebody please do that for me? You would realize that to meet 0.99 something, right? What does it mean? It means that half your friends, they seem to be sitting literally on the border itself, as far as you are concerned. right? So what does it do to notions of distance? If you have to go practically the entire space to meet even half your friends, means they have all gone very far off, isn't it? They have become. So, for example, in Bay Area, the way the housing situation is, if you want to meet your neighbor, you just extend your hand out of the bedroom and you can shake hands with the other one, isn't it? On the other hand, if you are in Wyoming or Montana and you want to meet your neighbor, you get into the car and drive for 1 hour, right? So higher dimensional spaces are like Wyoming or Montana, and lower dimensional spaces are like Bay Area. That's yes. So I didn't get that. Yeah. Yes, yes. I mean, see, I'm just oversimplifying it at the surface of the earth. Yeah, you're doing that. So, guys, so all I'm trying to do is give you intuition on higher dimension. So, in higher dimension, remember, when you go to your neighbors, you're basically looking at Euclidean distance. And Euclidean distance fails because everything is far apart from everything else. So then you say, oh my God, can I have some sensible notion of distance which is invariant of the dimensionality? Doesn't matter what dimension space I am in, it would. And it turns out that we are actually used to it. See, when you lie down and look up at the sky, you look up at this star, right? And then you look at a neighboring star, right? You say those two are close together. They are nearby. Are they really nearby? Actually, this star, in terms of actual distance, may be closer, and that may be like at the other end of the galaxy. But visually, angle-wise, they're close to each other, right? And by the way, how many of you are into stargazing? You are. Yeah. Have you read the lovely book, Turn Left at Orion? It's a lovely, you should do it. So anyway, stargazing is a beautiful thing. Uh, so one of the first things you do when you do stargazing is you first pick a few landmarks like Orion, the Orion's belt, right? Cassiopeia. Cassiopeia is a W in the sky, right? The Big Dipper, right? Pole star, yeah, pole star. So you pick up all of these big cirrus, the ones that are easy to recognize, and then you recognize the other ones by angle, near that, and so forth. And that's how you develop your skill set astronomy. And when you do that, the remarkable thing is you can walk out any day in the dark and you can tell what time it is if you know your stars. You can navigate by the stars as well as you can navigate in the daytime by the sun. Right? So anyway, what we are saying is, let's take a notion of distance. Suppose you are here and you look at this star and you look at this star and you say these two are close by. What is close by? It just means that the angle between them is small. How do you convert the angle to a number? One easy way is you can take either the cosine distance, right? Or you can take the dot product of these two vectors, A dot B. These two, both, you will see that they both are very aligned to the notion of angle between them. Two vectors which are orthogonal will have zero similarity. If they point in opposite direction, they'll have -1 similarity, cosine similarity, right? So this is nothing but A, B, cosine theta. So basically the heart of it is the cosine, right? That is why cosine works in any dimension. And it's very common to use cosine distance in this. Or why would, now you said, now, well, it's not really close to each other. And here comes the fun of machine learning. He says, how does it matter? I am imposing a loss function. Remember, I unshackle the weights. I'm going to train the machine. Where is my machine? I'm going to train the machine the way I like. So if I train it in cosine distance, what will it do? It will be forced to put two similar sentence vectors in a angle-wise close to each other, right? And other things far apart. So when you train this, it is called a loss function that maximizes this, what we just wrote here. It is called, this is called contrastive loss. Why? Because you compare A to similar sentence and say they must be close, and A to something random and say they must be far. And as you train the machine on and you keep changing your dials, the machine gets trained. And when it gets trained, what you end up with is something called sentence encoder, right? And how can it possibly learn to do that? Think about it this way. If you force a machine to position points like that, there is one and only one way that it can do that. It has to have natural language understanding, isn't it? There is no way a machine can put two sentences whose meanings are similar and a random sentence far apart unless over and over again through training, it has somewhere along the process learned to grasp the meaning, the semantics of sentences, isn't it? Right? That is the important thing. And transformers are, that's exactly what makes the transformers unique. They have natural language understanding. Right? Once you do that, now come. So now let's summarize what we learned. You can take your Isha. Oh, it's 500. Typically, BERT, for example, BERT base has 500 million weights. No, there's a process of gradient descent. It should be on the Tuesday class. So there's a whole process of gradient descent and backpropagation. So there's a systematic way to train the machines. They will learn it. Right? They'll reach the optimal. And when they reach the optimal learning, when they reach the optimal learning, at that moment, all the weights will be such. And this is the magical thing. You take a neural network and you stare at it and all you see are numbers. And yet the magic of this world is that bunch, that just box of neurons with its well-defined weights, somewhere in the weights is the understanding of all of human knowledge, all of human languages. It's the most magical thing in the world. Yeah, you can just download it. When you so-called download a model onto your code, when you write your, that is right. And so you just trained a machine. Let us recap what you just did. You created a machine which will, given A, similar to A and random A, will always create a vector space where A, SA, this is how it will go, isn't it? What is the implication of that? What you do is you take your hundreds of millions of documents that you have, right? You go through two phases. So this is a trained machine. We call it a sentence encoder. You take your documents, D1 to D110, let me just say 100 million documents that you have that you want to search over. What you do is you pass it through this box encoder, and what will come out? You'll end up with vector. These are called embeddings. The new word people use is embedding vectors. So I'll just use E. I could have used V. So both E and V are used in the literature, 10, 100 million. All of these vectors come out, right? And they all go and populate this space. They are all here occupying this vector space. Here I'm representing the vector space in 2 dimensions. But the real dimensionality of this vector space is actually, typically, it depends upon model to model. It will vary somewhere from 300 to 2000 dimension. So you can imagine that these numbers are beyond what human mind can grasp, right? Oh, no, number of documents. Let's say Google has 100 million documents. Your company may have just 1,000 documents. Data set, yeah. The size of the data set. 100 million is just the size of the data. That's why you say size, the word people use is size of corpus, the search corpus. Exactly. So, and that is it. So now comes the efficiency. Guys, hold on. Yeah, go ahead. Somebody has a question. Why don't you finish it?
Yeah. So this A, SA, and the RA, the A and SA are having a high cosine similarity, and A and RA are having a low cosine similarity, right?
Yes, absolutely right, Royal. That's how
So
it is.
this is the part of the corpus. The
All of this,
different.
no. Let me take that back, guys. See, that was the training phase. During training, you pass it with training data, which comes as triplets. Like triplets means you deliberately take a sentence and a similar sentence and a random sentence. You use it to train the machine. Once the machine is trained, now what do you do? So you go into the next phase. So maybe I should have emphasized it. So the box is trained. Now what do? You freeze the weights. You can't turn the knobs anymore. Are we together? So in machine learning, you have two phases, Roel. One is the training phase in which you do what we just did, ASARA, that game we played, right? And once we have trained the machine really well, you say that the training phase is over. You enter the inference phase, use phase. Means now that machine is ready to use in production. And how do you use it? You bring that machine over to your company and you take all the documents that you have, right? And you pass it through the machine. You don't know which is similar to which. You don't know. Doesn't matter. Because what does it do? This box, what is it capable of? For any text, remember what it is capable of is, even though you trained it with triplets, it is capable of just taking one sentence and creating one vector. Isn't it? Royal, are we getting that? For every document or sentence, document and sentence are synonymous words. For every document or for every sentence, it will produce its own vector.
Okay, so yeah, ASA and RA was the part of training for the sentence bot, right?
Yes.
And the corpus is a part of inference that we do to make a semantic search or some other applications.
Exactly. Okay. So now what we are saying, Royal, is that you download such a well-trained machine, right? And use it. And how would you use it? You would look into your company and you will notice that I have, so let's actually 100 million is a big number. Let's say within your company, you have only 10,000 numbers, 10,000 documents. For each document, you can create a vector now by passing it through this machine.
Yeah.
So then what do you do with these vectors? You hold on to this vector. So now you realize that converting a document to vector is expensive, right? But it's a one-time cost, isn't it?
Mm-hmm. Yeah.
One-time cost, you made them into vectors. And now comes the query part. Yeah, vectorization is completely independent of the query. Go ahead. Yeah, training data, yeah. Oh, yes. Good question. Yeah. Yes. So one question is, what is the notion of sentence versus documents? And the answer to that in the natural language understanding is the word sentence and document don't mean what they mean in common language, right? So, I'm reminded of a statement. I think it's in one of Lewis Carroll's book, either in Alice in Wonderland or Through the Looking Glass. Alice is confused. A little girl who's dreaming. She's confused. And she asks, who was it? Is the Cheshire Cat or Humpty Dumpty or somebody that, what do you mean by this? And she says, and he says, what do you mean by this word? And he says, this word means exactly what I want it to mean. Right? So in natural language processing, unfortunately, the word sentence and the word document, they have entirely different meaning than in common language. A sentence could be a word, it could be a phrase, it could be a real sentence with a punctuation at the end of it. It could be 5 sentences, a paragraph, or it could be what you would think of a whole web page or an essay. So when they say sentence, they actually mean anything, right? And likewise for document. Document could be a word, all the way to document is as like a whole file, the contents of a file. So in natural language processing, when they use the word, these words, sentence and documents, they're literally synonymous, right? So you have to remember that. Having said that, I will argue that how do you map the notion of sentence or document in natural language understanding to real documents? See, a real documents may have many things. It may be talking about the history of a topic, the technical details of a topic. So it's not a good idea because semantically there may be different meanings, different areas. So you need to chop it. You need to do something called chunking. So chunking is important. And we'll come to chunking. Right? Remember, that was phase 2, phase 3 of your homework. to do chunking. So chunk on semantic boundaries. Yes. Mhm. Encoder, using the encoder. Yeah, inference. Yeah. Yeah, that's right. Yeah, that's right. In encoder, you just pass it in such a way that you just pass one sentence at a time and you keep getting one vector at a time. Right? Yeah. Right. Yeah.
So Asif, I have a question.
Yes.
Yeah, so I'm confused about how this inference is the difference from fine tuning.
Oh, inference just means the weights are completely frozen. You're just passing input to the machine and getting an output. You're not doing any back propagation. See, this loss, there is no loss function. See, so the training of a machine is, okay, let me give you an idea of what a training is, guys. So let's take a little digression. What is learning or training in a machine? What you do is you take a box, all over machine learning, you give it an input, you get an output, y hat, right? It is like in case of numbers, it may be some function of x, right?
Yeah.
You produce that. This is called there is a name for it, the forward pass. Forward pass. Input went in, output came out. Are we together?
Mhm.
If you just stop here, you have just done an inference. Right? But of course, in the beginning, when you're training the machine, the inferences will be bad. Right? So what you do is training means you compare y hat to the actual y. So this is xi, yi. You happen to have a database of what the y should have been. Are we together? Let's say that you're predicting the temperature tomorrow at noon. You gave it some input of weather conditions today, and you got a prediction of what the weather tomorrow is. You predicted that it was 74 degrees tomorrow at noon. But when tomorrow comes, you notice that actually it was 68 degrees. So there is an error, isn't it? That error is considered a loss. So you would say, for example, in case of numbers, it is y minus y hat. This is a measure of the error, isn't it? If you're talking about temperature, you predicted 74, it was 68, you're 6 degrees off. That's
So
your measurement.
in terms of sorts, we don't have the y hat, right? So because we don't know what user will click based on the query. So that's the reason we just do the inference. Is that the logic or?
No, Royal. So just go along with me. Just think temperature, right? For the time being,
Okay.
I'll come to that. Think step by step, because so we do this. So now what you do is, in the magic of learning is that from this loss, you can do something called, there's two magical things. It is called gradient descent with back propagation. There are two magical things you do. And that is a slightly involved topic. In fact, that's a topic I'm teaching on the Tuesday Intro to AI course. But this is the magic, when people say machine learning or intelligence, this is the heart of it, gradient descent with backprop. What it does is it says, hey, this time around in this box, the knobs were dialed in like this. Maybe this knob was pointing this way, this was pointing this way, this was pointing this way. What gradient descent does is it says, you know what? How do I turn the dials in such a way that next time I give xi, I just get a prediction that is closer to the right answer? Are we together? Right. We somehow get a prediction that's closer to the right answer. And when you keep on doing that, that process is called training. Royal, are we getting that?
Yeah.
Training is the process of just changing the dials in the machine. At that moment, the dials are allowed to be changed. Now come back to your search problem. Search, the loss is slightly different. What you do is you give two similar vectors, A and SA. The machine will produce some vector. You check whether they are similar to each other or not. They will be a little bit far apart. And then you ask this question, how do I turn the dials in the machine so that those two vectors become closer to each other? Next time I gave these two sentences, they will land closer to the real place. So in other words, the question that you ask is, during training, suppose I give A and it landed here, right? This is the embedding of A. And I gave SA similar. And let's say that the embedding ended up here. SA was here in the beginning, right? This is the situation. This and this. They are far apart. Now you go and say, what do I do to the machine inside the machine? How do I turn the dials a little bit, right? So that the next time I give, and I go back and give the same A and SA, and let us say that the random A, the other random statement accidentally was even closer to this. This is the worst case situation, right? Not only is SA far from A, it is also random one is closer to it. So then what you do is you say, how do I change the dials in here in this box such that the next time around, let's say that the next time it goes like this, SA, A, SA, and RA, right? So you can do that. You can go change the dials in the machine such that next time you give the same input, this is the result. And that result would be, now the machine has improved. You would agree with that, Royal, isn't it?
Yeah, so basically the triplets of A, SA, RA. So
Yeah.
A is like for the input A. So Y hat
Yeah.
is like a SA, right? Which is similar
Yeah.
to A in the
Yes.
contrastive loss. Okay, I got it. Thank you.
That's it. That is it, right? And so that, folks, this is it. To train a machine is to change the dials. It's very similar to changing the dials inside this soundboard. Oh, that's right. No. All it says is irrespective of the input, the output should be a good prediction. Right? How do you internally make the machine such that it pretty much understands how weather works? So that whatever, suppose you say, okay, today's weather was like this, so what is tomorrow's weather likely to be? It will come up with the right prediction. So suppose it predicts tomorrow is going to be a really hot day, 90 degrees. Then it better be a hot day. The reality should be close to it. Are you getting that? Okay, guys. So that is how machines are trained. In fact, that is the heart of machine learning. Actually, if you really think about it, and I'll just take a small digression, think about what magic this modern time has achieved. You take a bucket of sand, you go to the desert, take a giant bucket of sand, metaphorically speaking, I'm oversimplifying it, come back home, do all sorts of chemistry with it. It's like you make a khichdi out of it, lay it out, and suddenly you have a silicon wafer on which you impose algorithms, your neural networks. And all of a sudden, this machine can learn, this machine can make predictions, this machine can understand human language. Isn't it? I mean, just think back. What is it that we have achieved? Isn't it absolutely astonishing? It is the most remarkable thing that mankind has ever produced. It has produced intelligence, effectively, a learning machine. Right? And it's starting out with what? Just walking into the desert and picking up a bucket of sand. So, well, that is it. That is about this. So now come back to our topic. So with that digression, let's come back and ask this question. You have these documents, D1, D, whatever, 1,000 or whatever it is. Let me just say N. N could be 1,000 if it is just your private collection, 100,000, 100,000 if it is your company, 100 million if it is your web scale company, right? Whatever it is, N is equal to whatever number of documents you have. You can pass it through this machine. So now you are in the inference phase. You're not training the machine anymore. Each of these documents, it will convert it into a vector, right? E1, En vectors. These vectors will all go and populate a vector space. There we go. Right? As you can see, it's populating a vector space. Now what can I do? I can pre-compute these vectors and store it. It's a one-time cost. Now comes the search traffic. When the search traffic comes, I get a query. What can I do? Query is another text, right? It's a document for you, sentence for you. You can convert this, pass it through the same box, and what will you get? You will get a Q vector, right? Let us say that your Q vector landed somewhere here. Q vector. Tell me, in view of this picture, what should be your search results? Right? You basically go in the neighborhood of Q and pick up all the documents that are here. Right? And the closer it is to Q, the better the search result. Right? You basically ask, which document does this vector represent? And those documents will be your search result. Are we together? And that is what semantic search is. Now, I gave you guys a demo last time. Do you remember how impressive the demo is? I'm going to go through the demo all over again after the break, but this is semantic search. Yes. Yeah. So yeah, let's work out. That's exactly where I'm going. So now think about it this way. What is the cost per query? You're comparing, once again, doing a similarity score. There are two aspects to it. With every vector in the document, in the corpus, isn't it? So the first gain is doing vector similarity is extremely cheap than passing two text through a transformer. Orders of magnitude cheaper, like 4 orders of magnitude cheaper, right? What can be achieved in 1 second, let us say, with the transformer, just as a 1 unit in comparison, can be achieved in 0.0001 unit of time as a vector dot products, because dot products are the workhorses. They have been perfected in Fortran and C way back in the 60s, right? So it is extremely fast. But then comes another piece of technology, which now, but even though it is a cheaper comparison, let me just call it cheaper similarity comparison, it is still order n, right? Do you agree, guys? It is still order n because you're comparing to all the documents still. Now, the magical part is you don't do n comparisons. What you do is you suppose, I'll just give you an example. Suppose you have already divided the space up in grids. Right? And all you do is you have a quick way of telling which of the boxes is this query close to. Whichever is the closest rectangle, you just check for neighbors in that. You realize now you're probably comparing, it's a much, go ahead. What do you mean by rank? No. That is what we're trying to find out, which is the closest vector. So what you do is, so guys, it's very simple. You have a lot of points. I'll make it simple in one dimension. Imagine that you have one dimension. There are 1 million points. But suppose I were to divide it into 100 units. Right? All I need to do is, suppose query comes and falls here. I can be sure that my neighbors can be in only one of these 3 boxes. Isn't it? And to the first approximation, even if I want to be rough and ready, I can just check in the box where the query falls, isn't it? So this kind of algorithm has been there since the 60s. It is called approximate, nearest neighbor search. Why? Because see, if you take this and only look at this box, not the neighboring boxes also, sometimes you can be wrong because, you might be missing things across the border occasionally. But approximate nearest neighbor algorithms, they are not about machine learning. They have been there in computer science for decades now, for 5 decades. And there has been at least a few hundred ways of doing it. And they have been getting perfected because all databases use it. Are we together? At some form or the other, internally use it. k-nearest neighbor, especially analytical databases. I say it as a person who worked in the kernel of one of those leading analytical databases in Oracle. So we use that. So now the state of the art is one of the algorithms that you, and the one that you guys will use is FAS, Facebook's approximate nearest neighbor search algorithm for vectors. Right? It is, so to give you a sense of how fast FAS works, it can work with a trillion scale vectors. Like imagine you have a trillion vectors, right? And you're doing search. You can still return results in sub-milliseconds. Even when you're pounding the system with hundreds of searches concurrently, right? So it should give you a sense of the might and power of modern algorithms and modern technology. What we are saying is approximate nearest neighbor search when you're doing on irrationally, just unbelievably large data sets, vector databases. Yet you can get, and even when you're pounding it with hundreds of concurrent requests, each of the requests will still return in sub-milliseconds with the nearest neighbor. So guys, do you realize what are we saying here? You can do semantically meaningful, much better quality of search than keyword search. Right? If you think of keyword search, that is order one. Let's go back. It's a hash table. You can just look up a hash table in order one operation. But we realize that semantic search was expensive. But through a succession of stages, by creating vector embeddings, then using approximate nearest neighborhood, right? We have nevertheless now gotten the cake and eaten it too. We got a far, far better search engine, and we somehow still managed to get lightning speed. Are we together? This is today's modern search engines. All the big guys have moved to it. While all the big guys have moved to it, like the likes of Google, etc., they all are using it, something like this. Variations of this. I mean, I've given you a simplified version. And obviously, you will be creating, that's your first project, to create that. Guys, you have to see the results to believe it, how utterly better it is. Last time, those of you who were here, remember, were you completely surprised at the quality of the results? Right? I'll repeat the same demo just to reinforce the point, and for new ones, new people. So today, obviously, is quite a bit of a repetition. I apologize, but it is for the benefit of people who have joined. But the results were absolutely impressive. And yet, if I can get the result in practically the same speed, you realize that you're looking at a complete revolution in search. You look at that and you wonder, why are people still, enterprises move slow, yes. In US, all companies drag their feet and they're like a decade or two behind the state of the art. But go look at your company. Most likely, you guys are still using Solr, Elasticsearch, OpenSearch, or something like that, right? You haven't moved to semantic search. Therein is the opportunity. Be a thought leader, go bring this in. Yes, a very good question. Somebody is asking me, may I have your name? Sorry. Girish, yes. Girish has asked me, so these vector databases are stored in GPUs, etc. See, the persistence is, of course, on disks. So you'll store it on SSDs. Fortunately, here's the amazing part. Because they are vectors, and vectors can be quantized heavily, compressed heavily, and at the end of it, right, you're just filling up an n-dimensional queue with these points. They're just floating point numbers. Listen, the storage is actually very small. And so in reality, what you do is when you run inferences and you're doing comparisons, you lift the entire vector database into the memory. And in fact, it fits into the GPU memory. So you are absolutely right. You're loading it into the very, very, very expensive GPU memory. And you can't do it in traditional search. You can't take the entire index and load it into the GPU memory. It will be horrendously expensive. But because it's a vector database, magically it fits into your GPU memory. A bank of GPUs will be enough. Right? Typically, one GPU is more than enough. And you're doing approximate nearest neighbor search on the GPU and returning it. And so this, by the way, as you do the project, you'll see there are two versions of FAS, GPU and CPU. And you can clearly see the GPU runs 1,000 times faster than the CPU. Right? In CPU, you can go for a coffee and get back your search results. In GPU, you won't even get the chance to blink your eye. And then you get the search results. Okay, that brings us to one thing, guys. Today, today is getting a review. Today was supposed to be the day I would hand over to each of you teams one powerful GPU-driven server. So here are the rules, guys. So people who are in this space of AI engineers, they work on one true operating system. Like it's like a religion. Like everybody believes that there's only one true religion. It's mine. Right? So in the world of AI, there's one true operating system. Linux, exactly. If you are using anything else, go make an appointment with a psychiatrist. Bad. No. So here's the thing, guys. People have managed to work on Mac. See, Mac emulates much of the Linux, POSIX compliance. Here's the thing. It mostly works. If you're smart, you'll get it to work. It never works as flawlessly on Linux because every single researcher who releases a model has only tested it on Linux. Mac is a close second. Windows is like, oh, hopeless. Right? What's that? Yes. So you can containerize it, Dockerize it, and so on and so forth. But see, you take a penalty. Like on Windows, when you do a Dockerize, what they do is they actually spin up a VM and your Docker is running. So first there is the horrible operating system, right? With its antivirus and God knows what else bogging it down, right? And spyware and telemetry. They're sending tons of telemetry back to Microsoft. On top of all that bloatware is a VM. On top of the VM is a Docker container. Inside that Docker container is your thing running. That's the definition of insanity, right? So just see, guys, we are giving you resources here, which has cost us $400,000. That explains why your tuition is what it is. Most of it doesn't come to us. We just want it to be the best place for you to learn this subject. And you cannot learn this subject unless you have access to good hardware. It's the nature of it. It's the entry ticket. It is the pound of flesh that NVIDIA takes.
Asif, you may want to just briefly touch on the electricity bill that you're paying every month.
Oh, yes, yes. Let me just put it this way. Just the electricity bill that we are paying every month here to run that data center probably exceeds your monthly pay, right? Your monthly salary. It is extremely expensive hardware, extremely expensive operations. And the only reason we do that is because we want it to be the place where, see, in your company, they won't give you root access to powerful machines. When was the last time you ordered a Dell super server with 1,000 cores, 100 cores, right? And a few GPUs sitting on it and said, oh, yes, yes, just the IT department said, yes, yes, sure, here it is. And by the way, you have root access to it. Do whatever you want. Anybody has had that lucky experience? Zero, right? Especially when you say, I'm going to learn on it, not that I'm taking a client to production and have revenue realization. Zero revenue realization, I want to learn, give it to me. They'll kick you out, right? You can't afford that, these sort of machines, these are expensive. So that's why we have these machines and we give you the opportunity. One more thing, Sukhpal here is raising his hand, go ahead. Yeah. Oh, okay. Epic, huh? Okay. Okay. So guys, one of the things, the machines that we built, there are two types of machines you'll get. One is a machine per team, right? So make sure you all have formed your teams. The machine that you get as a per team basis will have one GPU and a top tier CPU on it. Then you have another machine, which is a shared machine, cross team, the inference server, which has 4 GPUs, right? And has close to 126 cores just in the CPU itself, right? So we have some powerful hardware. In the beginning of the course, actually for LLM-1, you'll probably just need the server, the team server. How can you use your team server? First thing you do, I'll give you a clean machine. Now remember, guys, I give you a clean machine with root access. Why do system admins not give you root access? You can shoot yourself in the foot in 10 minutes, right? I'm
And
giving
others
you root.
too. And others
And yeah,
too.
so what happens is that, guys, you don't create headaches for us. We have 8 teaching assistants helping you, but we have even then a limited bandwidth. If we have to keep re-imaging your machine and starting from scratch, you lose time and we lose time, right? So do safe things. We will give you very clear instructions on how to proceed, which we are going to take you through. These machines are set up with Rocky Linux. They have the CUDA, the whole GPU and everything installed. What I will do is I will actually give you and your team normal accounts with one person having sudo access, right? So that before you install anything, at least ask all your team members and run it by us. Because the easiest way to screw up Linux is to just install a whole bunch of things that don't work together, right? And how would you connect to it from your home? Tailscale. Now, it's a code of honor, guys. On these machines, don't start Bitcoin mining or crypto mining. By the way, it's not a joke. 4 years ago, we found our clusters running extremely hot, right? And participants complaining that the machines were running very slow. They couldn't do anything. We are very mystified because you don't throw $400,000 worth of hardware only to hear your participants say machines are running very slow. Till we found crypto mining was in full progress. Right? So the fact that we give you root access, it's a code of honor, guys. We trust that you won't abuse it. Right? And trust me, guys, you do not get opportunities to good hardware just like that. And that opportunity will take away from you if you find that your team. So the whole team will be axed, basically. We'll give you the weakest hardware if your team cannot protect. So don't share your passwords. Don't share your logins to these machines with your friends and family. Certainly not your kids to play games on. Right? Be careful. Be careful, guys. You will have much better experience if you use these machines wisely. Are we together? Now, as for some people prefer working on their own machines because they have separation. You will start having separation anxiety. You do all this work on this good machine only to be told that one day we'll take it away from you. Right? So if you will soon start having separation anxiety. If you do, one thing you could do is you could reach out to Sukhpal. Right? Now, here is how it works. We can build a machine for you. The team machine that we have. So what happens is you will do some work on individual machine, some on the cluster. Much of the work for this course can be done on individual machine because this is the first boot camp. If you want a machine like that of your own, it costs somewhere between 3,000 to 6,000 based on how much it is. There are 2 ways of doing it. You can go buy your parts, and Sukhpal here actually helps you out. He's very good at putting machines together. For no cost, he'll just wire it up for you, right? And in front of you in half an hour, and you have your machine, right? Especially if you have some personal deals with NVIDIA or hardware companies, go get your own parts. On the other hand, he has some deals with companies. If you want a machine of your own, reach out to him. The experience from the past cohorts is more than 50% of the people ultimately start having separation anxiety once they know their machines are going to be gone, and they end up getting one for themselves. You can also go and buy one from Dell or from these people. And those are far more expensive because they cater to enterprise clients. And yeah, go ahead. Yeah, I'm coming to that. So I'll come to. So what are the alternatives? One is use the machines that we give you, which is enough for you to do this lab. It will be better than, for example, going to Collab and doing it. Collab has a pro version. Right? Google Collab. Google gives you a Collab, a Jupyter Notebook environment. The good thing with Collab is it's fairly inexpensive. I think the top tier professional version is what, $50 a month? $50 a month or something. They give you access to good hardware. It's temporary. You lose your work overnight. Right? So it's a nuisance. The other thing is, see guys, you want to be in this field, learn to work on the command line of Linux. This entire thing is command line driven world. Your fingers, right, they should have muscle memory. you can do in just 1 or 2 commands, what in Windows or a Mac, you go clickety click, clickety click, clickety click everywhere, right? It happens very fluently here. And almost all the people who are in this space, they are all command line people, right? The other thing is you can go collab. That's the second best option. The third is you can go cloud. You can reserve yourself, like suppose you have separation anxiety, you say, all right, I'm going to do all my homework in Google Cloud or Amazon Cloud. Let me put it this way. You'll end up raking for doing all of the projects here. It is quite likely you'll end up raking a bill that is 3-4 times the tuition you're paying for this course in the cloud. Because we are not kidding. We are doing real projects. The hope is that with these sort of projects, you're absolutely launching off to do your startups or leading AI teams within your own company. So we are not going to deal with toy data. You can do that. In case you go cloud, don't go with the marquee things like the AWS, Amazon, Google's, Azure's. They will fleece you to death. I'm on record. I shouldn't say that. Okay. They're very expensive. Go with.
I just posted a link for Dell Precision workstations. Those are coming out. The production has started. Sounds like just as an FYI.
Okay, yeah, guys. So look at this hardware. If you own a hardware, you have paid a capital cost. You don't have to pay. If you do the cloud, go with smaller guys like Lambda Labs, RunPod. They are far less expensive. RunPod is a very good choice. Like I remember that a lot of people from the last batch, they use RunPod. Let me write the name down. Right. Yeah. Yeah, guys, all you need is a 4090, right? So you can put a 4090 with enough hardware together with 4,000, 4,000 or something. RunPod is one of the lesser expensive ones and it's pretty reliable. A lot of people use RunPod. There is also a way to do serverless, just use it for the minutes you consume. Push your code over to that. I'll post a link to a few of these serverless frameworks where you can run your AI job. People have tried to use it with not as great satisfaction. RunPod is great. The only thing with RunPod is, guess what? What do you have to do with RunPod or with any cloud instance? Remember to stop it before you go to sleep, right? Remember, these are GPU-driven machines, right? When you are reserving a GPU-driven machine, you're paying many dollars per hour. These are not cents per hour. This is not, you're getting a general purpose compute instance, which is $25, $30 a month. This will, it's $10 an hour, right? When you look at this cost, even with RunPod and so forth, you realize why we have invested heavily in giving you the hardware. So use the hardware, don't abuse it, don't do crypto mining, don't give it to your friends to play games, and just have fun with it. 24 hours, it's yours, completely yours. Right? And by the way, if you need more compute, if you're doing your project really well and you need more compute, we'll escalate you from the way you ask. The first escalation is, we'll give you a cluster of 4 machines. Right? The next escalation is, we'll give you the super servers, which are banks of 4 GPU, right? And collectively. So we have all the hardware that you'll ever need. And that is exactly one of the big assets. So guys, just to give you the course, you have access to real human beings, people, teaching assistants who are helping you in this course, 8 of them. These are not ordinary people, right? Chandra, for example, he is one of the IIT toppers and with a very prestigious US PhD, followed it up with this. Kyle is an All India topper. And they're very smart guys. I'm the dumbest of them all, right? So use them. It is your resources available to you. Use the hardware, get started with it. I'll give you guys access to it. But for that, I need clear teams created, right? A good team is, so here's a simple rule to form good teams. Don't look for all strong people. If you take all strong people, you won't learn anything. Take a mix, right? Take a mix. and mix of talents. People, because see, somebody may be good at coding, somebody may be good at management. Will tell you that, no, don't design it like that, or this is going to take way too long. You're getting too ambitious. You need both kinds of people in a team. Form teams. Try to form a team of 4, at most 5 people. 6 is really, really pushing it. You won't learn much, right? And get started. Take a room. You see these rooms? They are all waiting for you. This is a land grab. Huh? Grab the best room. The only room you can't take are the front 2 rooms with windows. Right? You can take any of these rooms. That room, therefore, becomes your room. You can leave your stuff there. You can come here any time of the day or night. Typically, I don't come. I'm not here before 11, right? Because I have a lot of India meetings to do. This place opens later in the afternoon, mostly. But after that, it stays open every day till late night. Fridays, I leave early, right? But other than that, it stays open. You can work, especially with Tailscale. You can connect from anywhere. But having said that, I will strongly encourage you that as teams, see, the guys who really went ahead and did startups and did very successful things, one of them, by the way, didn't do startup outside. They did startup within their own company, traditional big company. And I mean a really big company that I can't name for privacy reason. They founded the AI team there, right? And this is stories that have happened in multiple places. What they would do is, even though they had a wonderful company with a lot of real estate and office space, they would all come and huddle here in this room. The moment the office was over at 5 o'clock, 4:30, they would all drive here and be packed in that room. Right? So people do that. They have an atmosphere. Anytime you come, you'll always have coffee and snacks waiting for you. And it's a pleasant atmosphere. You learn from each other. Create your social learning group, form your study team, and be actively engaged. As they say in America, half of success is just showing up. Do get engaged. And the project, I'll review the project. For those of you who are new, I'll repeat it. Obviously, I have to show it to you the first time. And we'll go over it in a little bit. Right? Let's take a break. It's going to be 1 o'clock. I'll go and get lunch for all of you. But are we clear? Those of you who are new, are you getting a lay of the landscape? Right. And our days will, so today was unusual because it was a long review of what we did, or it's for the benefit of people who have joined new. But in future, we typically give about half an hour to reviewing the last day. Then we go into the new topic. We do some demos. Then we do demos are show and tells of progress of the teams. Then we go into very specifically the subject matter. Again, we do research paper readings. We do Cambrian explosion. So it's very structured. We will do that structure perhaps, but in a little bit more condensed way because of the unusual nature of the second day.
Asif, can you talk about the teams for those who joined new?
Oh, teams. See, guys, I thought I did. You need to form teams of, Atish, I'll come to you. If you try to create a team of less than 5, 4 is a perfect number. 5 is okay. 6 is pushing it. 7 is, I think I'll steal chairs out of your office so that you can't squeeze 7 into it. Right? So stick to that. As a team, you'll work together. Guys, there is a really good prize at the end of the winning team gets a big prize. Oh, it's a mystery. Yeah, but let me just say that it isn't just a little toy. It's something good, right? And do your projects well. Work in teams. People have learned a lot. Madhu, would you like to say something more on teams?
I was just going to recommend, like whoever's joined new, welcome. Find your team member. I think the 4 would be the right size, in my opinion. If you can form it, but there's always an option of doing it independently because you learn quite a much, and in a team environment, of course, you'll collaborate a lot, but being independent, you could also do a lot of things. You might run out of time, but you'll learn a lot of things. Whoever's joined new, just keep messaging in that Slack channel and ask if you can you can join any of the teams and be considerate for the new members, whoever started forming the teams.
So guys, yes, thank you, Madhu. So it's Discord. Guys, anybody who is not on Discord or hasn't joined the LLM1, we need to make sure you join that. Guys, use Discord. The first order of business, while I go and get your lunch, please form your team, because when I come back, I would like to start giving you the hardware. Kate? Open.
Hi, Asif.
Better in the afternoon. Come in the afternoon. Friday evenings, I leave early. Yeah. Go ahead, Srirang.
Yes. So if we know everybody who is remote, we could
Yes.
possibly, I know Jyoti and we went in a team, but if we know who's everybody remote, and perhaps we could do a
Kavita is here. Kavita is remote. But I was thinking, so Kavita is, so here's the thing, guys. Remote, don't make a team of all remote. It will be a really bad idea, because what if you want to reboot your machine physically? You need to have somebody here. So make a mix of remote and in person.
Okay.
That's what I would recommend. And Kavita, you are in the same team with Atisha. Just thought I'll let you know. Atisha, could you reach out to Kavita? Your team was too big. Pixel's too big. Oh. Okay, so there's a lot of horse trading going on. I'll come to know, whatever. Get me the final list of teams by end of lunch, guys. I will go get lunch for you. So our plan in the afternoon is we are going to go through the demo of semantic search, which was quite useful last time. But I'll do it very quickly, the same demo. Today, we will cover new topics, guys. Today's topic is, in the space of semantic search, what else can we do with embeddings? We can do document classification and document clustering, right? Which is very common. And then we'll bring in a large language model. We'll take a first baby step with prompt engineering, a systematic prompt engineering. Why is that? Because when you put semantic search together with this, you get something called RAG. It is the dominant application of Gen AI these days, retrieval augmented generation. We are making progress towards that. But before we make progress, we still have a few things to learn. We'll learn document clustering, document classification. We will also learn dimensionality reduction. So one of the questions that must be nagging you in the mind is, how do I visualize these vectors? Right? I can't visualize a 500 dimensional space. Well, it turns out, believe it or not, there are ways to visualize it. And we'll learn those visualization techniques. You can actually see your vector embeddings. We'll learn about that. And we'll learn about something called a cross encoders. So what happens is you have some benefit from semantic search, some coming from the traditional search. And how can you take the best of both the worlds to have a really, really powerful search engine using something called a cross encoder? And so we'll learn about cross encoders. So we have a lot of powerful techniques, practical techniques to pick up. We'll talk about that. Hang on. I think Atisha has been waiting for a long time. Go ahead. Yeah. Discord, help. Guys, anybody needs help, literally go to the help channel of this and say, can I please have some time from a TA? This is my problem. Describe your problem so that people can determine who is the best TA for you. Yes. Absolutely. Absolutely. All of those are part of this. See, this course is very thorough. There would be nothing left under the sun we won't cover. Yes. Yeah, we will do that. Right. See, at the end of it, right, you would have recreated a complete vector database, a complete RAG pipeline, high performance, of your own from the ground up, instead of just using, let's say, Llama Index or something like that. You will do that also at the end of it. But the idea is not to just use libraries, but to understand what's going on under the covers and build it all. So you will learn about semantic chunking, very much so. Yes.
Asif,
Yeah, yes.
recording is still going.